Okay, I'm going to start from the beginning and do the process for doing regression in SAS Enterprise Miner. Assuming that our first step is already completed and that we have imported a set of data that is randomized, the next thing we need to concern ourselves with the veterans data set that we've worked with in the past is that we know that income has been improperly reported, that in many cases it says 0 rather than missing, which is what the actual value should be. And so in order to fix that, we put a replacement node on there, and we have to do a few things. We have to do missing as the thing that we're going to put into the column that matches what we're looking for, and in the interval variables area we're going to say none, because we're going to do this on our own. We're going to go into replacement editor, and where it says income we will say user specified, and for anything under 1 it's now going to be replaced with a missing value. We get confirmation here that there were 2,357 values that were replaced. The next thing we want to do before we're using any of our modeling nodes is to split the data into training and validation data, because that allows us to test our model creations out on the validation data that it hasn't seen yet. The model's created with the training data, and then it's tested against the validation, and then we get reported back to us how well it's doing based on that data that it hasn't seen before. So we'll do 50, 50, and 0, and then run that. Now at this point we might be tempted to go straight to model and find our regression and put that on there and attach that to the data partition. However, before doing that we need to consider whether our data meets the criteria for being analyzed as a regression. And one of the things we have to be concerned about is whether or not there are missing values in our columns of data. And if there are, then the default behavior is to throw that row of data out. So if you have if 50% of your data has a missing value somewhere in a row, then that data goes away. Now, and that also is problematic then, not only for creating your model, but for analyzing a later model. At this stage, with just creating the model, what we want to do is take our existing data and we want to add in values where there is no value currently. And so the way we do that is we go under Modify and grab this Impute node. And what this is going to do by default is it's going to replace the class or the named variables with the thing that appears the most often. And for the interval variables, it's going to replace the missing values with the ones that show up the most frequently, or they're actually the average of that set of data. So if the average age is 18 and there are missing ages, then any missing ages will be filled with 18. Now the thing we need to change is we're going to go down here to indicator variables, and in addition to creating a new variable which is going to be the imputed variable for the missing ones, we're also going to include variables in our data set that indicate whether or not a variable has been imputed in that row of data. We can do that two ways. Either because one thing we can do is we can say something has changed, but we won't indicate where. Another thing we can do is we can create an indicator variable, a 1 or a 0 variable, and kind of name it after every single column that was missing, and then we know which column was missing. So we kind of if we have a missing variable in a given row of data, this approach is going to create two different variables for us. One is the new variable that was filled in, and the other one is going to be a 1-0 saying which column was changed. And both of those become inputs to be tested whether or not either of those affect the outcome in the regression. So after running the procedure here, it looks like we had three different variables that had missing values in them. One of them was the one we just created in a previous step, and then so each of those results in two more variables. We get this new variable over here in the third column, which is the updated value, and that's what we want to do in our predictions now. So it's identical to the previous column of data, except that now it has averages filled in where it used to be empty. And then we have this other column of data with the M in front of it, which is just a 1 or a 0 saying, hey, there was a change that happened in the data where it used to be missing. Okay, I dragged a regression node down and connected it, and I'm not going to change anything at this point. I'm just going to let it run with what it has and see what happens. And so as I compare this particular model in terms of its efficiency and accuracy compared to something else like a decision tree, I would look for things like average squared error and misclassification rate in the validation data set, and so I would use those numbers and compare to future models. Now the behavior of a default regression node is that it's going to look at every single variable in the model at the exact same time. It's not going to try to get rid of any of them, and it's going to say subject to the presence of the other variables. Are any of these significant, meaning do they indicate that they're causing an impact on the thing that we're predicting? And kind of the intuition behind this is if you put in too many things, some of the things that matter aren't going to show up as well. And so that's where our stepwise procedures and such come in. If we scroll down in this data set far enough, then at some point I'm going to pause and find the right spot in the data and come back. Looks like the answer was near the top. First, to test the overall model, and it says for this that it's far less, the probability is far less than 0.05, so we think that something in our model matters, and that on the whole our model matters. But in terms of which variables stood out as being impactful, it's not very many of them are. We can see that this one is, because it's less than 0.05. That's usually our rule of thumb cutoff for saying whether or not something matters. And so there really, and anyway, there's just a few things in here. We can do better than this and get better accuracy if we narrow down our variable data set. So let's see how we do that. Alright, what I've done now is I've added on 3 more nodes of regression and had them perform their procedure differently to select variables that would be useful for predicting outcomes. I really only made one alteration in each case. If I go down to model selection on each of these, I can select forward, backward, and stepwise. And so kind of the thought process here is with the forward model, it looks through each variable to see which one at a time, and then incrementally, sort of like when we're building our decision tree, it selects which variable is going to be most important to our model, and then it puts that one in there, and then it runs the model again and looks for the next variable that would also be important, and it continues to do that until there aren't any other significant variables left to add. So it starts at basically no variables and keeps on adding them. The backwards procedure does something a little different. Sometimes it'll come up with the same answer and sometimes it won't. Instead, that one starts with every variable in the model. You saw how that performed before, where only 3 variables came as significant, and then it starts removing the least important variables one at a time. And as it does that, other variables start to become more impactful in the model, and it'll pick that up. So it does that one at a time until the only thing left in the model is stuff that is significant. And then stepwise does both of those procedures at the same time. It does a forward and a backwards procedure, so it'll let things in assuming that their value is significant enough, and then it'll kick it out assuming that it's low enough. And in addition to just going with the defaults, you can also change the say don't use the defaults, and then go in there into your selection options and make sure you do three things. Make sure you do plenty of iterations, like 30, and then I would typically recommend that you have a looser input to the model criteria than kick out criteria. And as we performed in class with this data set, the defaults are 0.05, 0.05, but if we go a little bit higher than that, then we actually tend to get a better model in terms of when we look at the results. And I think it would actually be useful to discuss the results that came out. If I look down in my stepwise regression, at some point it says that it's done, that no further effects were useful, and it selected, the selected model is the one that happens at step 8. Just kind of some background information. This number is probably getting higher and higher, this chi-squared ratio, and the higher this gets, usually the higher the significance of our overall model gets, meaning that it's performing better and better at predicting an outcome. And right here under type 3 analysis of effects, these are the variables that are important in our model. Now, this is more than what we had before. In our first run we only had 3. Now we have a lot more that are useful in predicting things, and we're going to have greater accuracy because it's selecting this model based on how it's performing against our validation data, so that gives me a high degree of confidence. Another thing for us to look at and talk about is the practical significance of the variables that were selected. So generally so if I go down here to the odds ratio estimates, a couple things to discuss here. One is any value that's greater than 1 is actually increase. It means that a unit increase in this variable, maybe it could be, in this case it's not age, but if it were age, every unit increase, like going from 18 to 19 to 20, results in this right here of an increase, the number behind the 1, of an increase in the likelihood of getting a yes answer in our outcome variable. And similarly, we also get a reduction for each input level decrease for these variables if it's less than 1. So so a large number here would indicate this would get kind of multiplied by that percentage, and it keeps on decreasing the likelihood of getting a 1 or a 0 on the other end. So greater than 1, good. Less than 1, it reduces the likelihood of the outcome. A couple other items to talk about. For categorical variables, it actually compares different variables and saying, hey, if you're this value versus that value for a particular column of data, then your value goes up or down. And the way that this typically works is that one value will be selected, and it looks kind of like the S value was selected here as the default case, and then so compared to getting an S, you can go up or down from there depending on which other categorical item you selected. Now, one that's a little bit confusing perhaps is this one that's a 1, because I said if it's greater than 1, that increases your chances. If it's lower than 1, it decreases your chances of getting the outcome you're looking for. And the reason for that is that the variable here for median home value is such a large value, because it goes into the hundreds of thousands, that a 1 unit increase isn't very meaningful. So if instead you were to collapse that into much bigger changes in value, like 10,000, 20,000, 30,000, then you would get a larger value here. As it is, what happens is if you bring this out to a 0.0000, somewhere out there'll be some number that's greater than 0, which means that for every dollar amount that's greater in the person's home value, there's a really tiny increase in the likelihood here. It's greater than 1, we know that. We just don't know where it starts picking up the impact. But if you were to, again, change the scale of the variable, you would get something different here. Maybe turn it into categories or much bigger brackets rather than just a value that goes from like 1 to hundreds of thousands.